Let's have a look at text representation. Today we'll be having a look at what it means to have your text represented as one-hot encoding or in one-hot encoding schemes in bag of words, as word embeddings, and then we'll also be going into a bit more depth regarding transformers and BERT. Transformers is one of the foundational blocks that a lot of the state-of-the-art systems nowadays work on. And yeah, BERT also applies transformers and does some interesting stuff with them. So let's get into it. So we want to represent text as words. So the idea behind it is that a text document is a combination of words. So let's find representation for these words and then combine them somehow. So what's the idea behind this? What's the goal? What do you want to do with it in the end? We want to analyze documents, mainly in relation to each other. And we'll see that it's important that's also in relation to each other, because when we have one scheme that we define, it's not necessarily compatible with another scheme that someone else defines. And as such, we are kind of working in a closed world assumption there. So, as we said before, a document is made up of words. Today we'll be taking this kind of example here with just landed in Tokyo, can't wait to explore temples, cherry blossoms, and sushi spots, and travel makes life magical. Yes. So if we wanted to just see what words are in this, we add all of this here into a list where we want just to have the unique words in it. We don't care about what spot these words appear in. We just want to throw them all into a list and just have each word appear in it once. Here, note there's some simplifications that we're taking care of here. We don't take punctuation into account here. We also ignore the emojis, even though depending on what kind of application you're working on, this kind of assumption can be fatal. For instance, if you want to do some sentiment analysis or some disambiguation, for instance, it might help that for sushi, for instance, you already have the sushi emoji here, and for travel makes life magical, in order to figure out that people are actually being genuine and having fun and enjoying themselves, it might actually be useful to know that, oh, look, there's emoji with the hearts around it, so it's totally what they mean. What else? Oh yeah, we also ignore the casing in our case. Like there are systems which do it both ways, like where they at first do it, okay, we don't care about the casing, whether it's upper or lowercase, and then afterwards also train with the casing, like where the casing is actually relevant on whether, for instance, you're at Tokyo with a capital T or all in caps and such. But yes, now we have our representation here. We have all the different words that appear in our document, and we want to somehow represent our document, right? So for each entry here, we just have a 0 or a 1, but since we just created it all from our document, there will be a 1 in every spot. So we want to encode our document in relation to word presence. Like, is a word there, yes or no? And here in this case are, in quotation marks, vocabulary that we're using to mark whether a word, like what our entirety of possibilities of words are, is the contents of our message. So as you might figure out, when we use this kind of representation here, we just put a 1 everywhere. That doesn't really give us any information on the word order. It just tells us, okay, this word is in here. So it doesn't really mean very much when we just do it based on one message, or when our vocabulary is just the contents of our message. So let's see what it's like when we actually have multiple, like a larger vocabulary rather. So let's assume we have this kind of vocabulary here that might continue on to be a lot bigger. It could be the size of an entire dictionary, for instance, like of an English language dictionary or some kind of encyclopedia. So we have our document representation and we want to map it to vocabulary. So for each entry here on the right side, we just add our value of 1 to wherever it would belong here in the list. So we try to figure out, okay, we have landed here and we are looking for the specific spot within the larger vocabulary where landed is, and what was 0 is now 1. We just flip it from 0 to 1, and the idea here is that this allows us to represent a document in the fashion of saying, hey, is this word in this document? Yes, no. And as you might see, we just have ones everywhere. Well, ones or zeros. So France didn't appear in our document, but landed, Tokyo, and sushi did appear. So there we have a 1. And this is what's called a one-hot encoding. Namely, we want to encode a document in relation to whether a word is present in a given vocabulary. Yes. So moving on. Well, we've shown that we've now encoded our document in relation to vocabulary, and now technically have a document representation for this, a one-hot encoding, if you may. The problem here is that it becomes pretty untenable once the vocabulary size grows beyond a certain size, really. So if you had, for instance, the entire English language as vocabulary, it would be taking up quite a bit of space just to have a single document in it. Not necessarily the greatest thing. Also, here we don't really get, there's a few aspects that we're missing. For instance, there's word order is completely missing. Like we lost a lot of information from our original document by coming to this kind of, in quotation marks, simple representation. Now, let's see what else we could do. We could be doing a kind of bag of words representation. Well, the idea behind it is that rather than just saying, yes, this word is present, or no, it's not present, we count the frequency of the words. And the frequency, for instance, for this document here is, you see that wait appears once and twice. Tokyo appears twice, once there, okay. Travel appears twice too. I appears 3 times. Yes. So we have the frequency mapped. We have the words as well as the frequency mapped together. The advantage here is that, well, when we represent that way, we don't just have like a 0, 1 of, okay, this is in it and this is not in it. This way, word repetitions actually gain meaning. The more you repeat something, the more important it might be. And that's the kind of thing that we can also store in our representation this way. And there's a lesser loss of information, for instance, the text length. If, assuming we have a perfect match with the vocabulary, we could just add up all these frequencies here, and then we'd know how many words we'd have in a document. As such, if we train a model based on this kind of representation, we could also deduce a certain kind of, in a certain way, we could also have implicitly the length encoded in it. But yes, we still have a bit of an issue that word order is not considered. But we've gotten a lot better compared to the one-hot encoding from before, where we just had whether or not a word is within a document or not. So we see that, okay, just to be complete, we see here that the entries with 0 means, okay, France is not in our input document that we now encoded. So a challenge that we still have is that, okay, we have, this is our vocabulary. All of these entries, France, wait, Paris, Tokyo, travel, I, and so on. And that means that our vector, or our vocabulary size would have to, whenever there's a new word coming in, we'd have to increase that size as well. And well, the English dictionary is pretty large, and it would take up quite a bit of memory if for each and every document we'd want to represent it that way. So how about we limit to important entries by just removing unimportant ones, for instance. And there's ways for doing that. Yeah, there's ways for doing that, but we're not going to go too much into detail in that regard. Instead, we'll show how we can actually represent documents in real valued fixed length vectors, and where this particular vector encapsulates word meaning. This is called a word embedding, where you want to embed the meanings of a word into a real valued fixed length vector. For instance, you have systems that use dimensions of 512 or 256 entries. It's usually a multiple of 2, like a power of 2, rather. Yes. So what are methods that are used for word embeddings? Well, there's neural networks that are used. There's also dimensionality reduction techniques and probabilistic methods, but to be frank, the neural networks have reigned supreme recently. So in the following few slides, we will be presenting a very simple text embedding procedure on how we could encode a document in a kind of embedding, but in a very simple fashion. Moving on. So let's assume we have a vocabulary which, well, we'll simplify it. We have a vocabulary of 5 words with Tokyo, Japan, sushi, Paris, and France. And each of these here will represent by a vector. So the Tokyo vector would be 1 followed by zeros, like 1 on the first spot, followed by zeros. Japan would have a 1 on the second spot, followed by zeros, and so on. For sushi on the third, Paris on the fourth spot, and France on the last spot. So for every word within our vocabulary, we have representation, we have an embedding, in quotation marks, that we will try to use to represent documents with. Ideally, you'd want all kinds of important words to be in the vocabulary and potentially ignore all the non-important ones. And here, let's say we just consider these the most important ones, and we don't care about the rest of the information within the document. So we're still working on the same document we had before with, there's Tokyo. Yeah, actually it's 4 sentences now. It's a slightly larger message. And how could we represent this kind of message, or how could we encode this kind of message in a way that we're incorporating these different embeddings? Let's have a look at it. We will just take the various embeddings and sum them up together. So the idea here is the document is the sum of all of its word vectors. So we have the vector for Tokyo that is added here twice, The vector for Japan, nope. Japan does not appear anywhere here. The vector for sushi appears once. The vector for Paris doesn't appear, and the vector for France doesn't appear either. So the prior embeddings, these 5 here, we just add Tokyo twice, sushi once, and so we end up with this kind of document embedding. Yay! Right. So we found a perfect solution, we're done. Not quite. So we have some issues with our simple approach. Well, the positional values, they grow with the text length. So the value in the first spot, where we had Tokyo, for instance, that just grows more and more the more often it is added. So, okay, so it might be important, but might not be as important as the embedding might represent it as. Further, we're not taking into account any order. We're just taking the words as they come into it, just the frequency. So there's no way for us to properly deduce in what order they may have appeared. In our case, there's many vocabulary items that are also ignored because we just took 5 different ones and we just chose the 5 most important ones for our task. And well, document length is also not taken into account. And here this is the important one that's actually leading us to the next slide, is that, well, discrete values only have very limited expressiveness. Because we can only use discrete values, 0, 1, like numbers with an n, we are forced to have one position represent one word, practically. So what would be a good solution to this here? Okay, let's use the average. Let's just add all the word vectors together and then average over it, and then that way, even if we have a word appearing more and more in it, it would kind of be averaged out over everything and should be fine, right? Well, in some simple embedding schemes, once you have word vectors that are nicely defined in a real valued space, you add them together, you average them. That's oftentimes a simplification that kind of works. Depends on what you're doing with it, but usually that can work depending on use case. So another potential solution, well, unknown, but as so often in machine learning, let's just train something. Let's just train some embeddings for us, and then we'll figure out the rest later. So if we train something where we want the semantic meaning to be, well, loosely associated to some defined simple arithmetic operations, oftentimes such as the sum, or, well, a sum like a positive or a negative sum, so that you can subtract vectors from each other in a kind of way that semantically makes sense. That's something that's been researched quite a bit with embeddings, where they've also been trained towards, because that's how you get them to be the way you want them to be, the embeddings, by defining a function by which to compute them with. Well, so let's say, for instance, we have now again our prior embeddings from before for Tokyo, Japan, sushi, Paris, and France, but now they look this way here. So they have real values, and as you might see, we want these entries here to have some kind of meaning. For us, for humans, it might not be immediately obvious, but they might have a certain kind of meaning that's implicitly in it. For instance, Tokyo and Japan, how they stand to each other, you might have a relatively similar relationship between Paris and France, while France and Japan being different, like relatively different, and Tokyo and Paris as well. So we want to make sure that these words still encapsulate the meaning that they were trained for pretty well, like as well as possible. Like we want them to be different enough from other entries to be recognizable as themselves in space, but we want to be able to apply certain kinds of simple operations on them. So for instance, we want semantically similar words to have similar embeddings. For instance, we want Tokyo and Paris to, as we see, we reordered them slightly, so it's easier for visualization purposes. So want Tokyo and Paris to be kind of more similar to each other, and want Japan and France to be similar to each other. Because intuitively, it can make sense to have Tokyo and Paris be relatively similar because they're both capitals, like world capitals, but they're still different entities. Same thing for Japan and France. They're both countries, so they might also be conceptually or semantically similar. So as such, you can tell that the difference between the entries here is not very large necessarily. And yeah, we can do some kind of operations with it. One of the more famous, well, this is not a famous example, but this is the famous idea behind it. For instance, that we take, because we want there to be semantically similar words to have similar embeddings, we train them as such so that we can do all kinds of fun operations with them. For instance, you can say that, okay, if we have Paris, but we remove France from it and we add Japan to it, then that should be more or less equal Tokyo. So here we have a kind of visualization of the different vectors. So if we now take Tokyo over there, and we say that, okay, it's Paris, but we remove France, but we add Japan, and then it should get to Tokyo. This is the idea that's behind the word embeddings, as you may have it. So there is an approach that is relatively simple, but it's mostly historical at this point. It's relatively simple, but was really set a huge precedent, to put it that way. And namely, it's called Word2Vec. It was developed by Google AI 11 years ago at this point. So in the grand scheme of things, not that long ago, in machine learning terms, ages. And Word2Vec had two different schemes that you could train it with. One was the so-called continuous bag of words. Okay, bag of words is what we had before. The CBOW scheme and the skipgram scheme. So one was, okay, from the words you have around you, you want to estimate the word that you have, and then you do it the other way around. Okay, which ones are related from me? And these are the two methods that were presented there. I'm not going to go in detail into it, but if you're interested, please have a look at the Wikipedia entries or the Towards Data Science article I just linked to here. So, moving on to transformers.